something about the notion of and the figure subset of what this word factorization is doing. So let me start with the definition. We definitions. All these definitions will have a very similar structure. First is factorization space. Kevin, make that where you're involved. You speak up. What? Thank you. Keep it up. Yeah, okay, so factorization space. So it will be a pre-stack over the rand space. So relate utilization y rand. And it should be equipped with the following structure. So equipped with the symbolisms. I have two disjoint points on the Rand space. So they correspond to finite subsets of x which are disjoint. The fiber of this y at this disjoint set of points is supposed to be identified with just the product. The fiber at x and the fiber at y. So x prime. And so secretly we should think that y is, kind of determined by what happens on the curve with some additional structure. So if I take the fiber from y at say x1, xn, this is supposed to be the fiber of y at x1, y at xn. But of course, the key maybe additional data that makes this point variability kind of illegitimate is that these points are not together. That really carries some non-trivial information. Okay. Now, this point, yes, but this notation, okay. I'll write it for x and x minus to the round space this way. Okay. Any other questions about this? Okay. So now I can kind of repeat the same pattern with the word space. So factorization category. So now this will be a sheaf of categories on the ranges. I'll denote it C, rank space with exactly the same kind of structure, except now the fiber at the disjoint union of two disjoint sets is the tensor product. Yes, and it's here's a very basic example. So if you have any factorization space, I can do some categorical construction to it, like taking d modules d of y ram, which refer to the d of y from ram, for y a factorization space. Or we can apply, there's some maybe fancy version of encode that appeared in the previous talk in the start. Yeah, I don't like that. And okay, and this is usually where factorization categories will come from. They really usually come from something dramatic, like factorization space. And one more piece of notation. So a really, really silly example of factorization space is the rod itself. So like the fiber of rod over itself is really a point times point is point. And so in that case, you get a very silly factorization category, which I'll denote that one. The reason for this notation again is that the fiber of vect drawn at every point drawn is vect tensor vect is vect. Factorization. Okay.
You need to specify the equation behavior somehow anyway.
That's well captured by the fact that it's really living over the bond. So like if you want to define such a thing, you cannot just specify a value at every k point of the bond space. You really need to as a T stack over bond or as a Q category. Okay. Now yes.
What's the tensor part?
The tensor part of two categories. Well, it's a certain operation with the following feature. So if you take quasi-clone of, let me write this. So this way, so you take A modules, this is a category, and you tensor with B modules. You'll get modules for A tensor. It's not a definition, but okay, that's like the proto family.
Sorry, by sheaf of categories, you mean like a sheaf in
What's
three
the
stacks
sheaf
over
of
runs?
Okay, yeah. So what do I mean by sheaf of categories over P stack? So let's say Y is a P stack. So the way you define a sheaf of categories, well, okay, no, let me not say about this story. So one thing that was discussed when the Ron space was introduced is that it's built from powers of the curve. So Ron, we said, was the limit of x to Ron to the I, and whenever you want to define, so this means that whenever you want to define something over the Ron space, you only need to say what happens over each of these terms compatibly. And so if I want to give a sheaf of categories over the Ron space, I have to give collection of sheaves of categories over x the round to the I. So I just need to tell you what sheaf of categories this is, and that's x the round to I is a modulo category over the modulus. But you should really think that a sheaf of categories of the random space associates to any point on the Ron space a category somehow varies, correct? Any other thing?
You don't do that for visiting ones.
Yes, but like when Ron was defined, it was already of that nature. So yeah, okay. So now there's the notion of finally a factorization algebra. And this notion actually makes sense inside any factorization category. So I'll get some reticence. Factorization category C Ron. And this is, well, it's a D module, A Ron on the Ron space. Or if I want this more general concept, I have to give a global section of this sheaf of categories. The global section. With, well, factorization isomorphisms, which are exactly like those. So I should require that the x is going to be an x term is isomorphic to the x and to this. And if I'm working in a more general factorization category, this isomorphism has to happen in the fiber of this sheaf of categories at this point. So in general, this would happen inside here. Let me give the silly example. The silly example is well, okay, so the silly example here was just like Ron itself, and then you take back to Ron. So of course, if I take the dualizing cube on Ron, so it's the D modules whose fibers are all just K. That's a factorization algebra for solutions. Factorization.
Just to know where things are living. So this algebra is just going to be like the Cartesian section, this fiber from C around to around that.
Yes. Okay. So now let me maybe mention another, well, maybe the other mechanism for producing factorization algebras, which is bifunctionality. So let's suppose I have a functor between two factorization categories, V1 and V1. So this is a functor between cubes of categories, and you can ask that this functor is compatible with the factorization structure on C and D. So it's the factorization functor. If, well, okay, the diagram you expect from me does be D x which will give you x prime, C and C is prime. This is F. This point. And then take the tensor product of at two. And then the very silly observation is that if you plug in a factorization algebra to a factorization functor, it's still the result will be a factorization algebra. So it's for me stated as a proposition, even though it's kind of tautological. Factorization functor. Stems. Factorization algebras. Okay, so that's like the end of this barrage of definitions for now. And now I want to explain maybe one example, which is maybe a basic example, but it's still interesting. We will be brave and use this word. So let me produce for you first a factorization space. And actually, this is, well, something we've seen before, but maybe I'll review it in a slightly more general context. So before this, let's say I have an S point of the Ron space. So we have this picture of S with X, and I guess we have a family of, well, maps from S reduced to X, and we can take their graphs. And the union of the graphs is a finite subset of X which varies with S. And we'll call this gamma. And then, so we have this finite subset of X which varies with S. Now we can consider the formal disk at this variable finite set. And that's like, okay, something. Picture like this. Maybe. And this formal disk, I guess it's usually denoted DS. So, one more. And then there was this issue that you really want the affine scheme version of this. The reason that we want the affine scheme version is to also consider the puncture disk. Okay, just remove the puncture. Punctured is here. So this is now finite collection of puncture disks, which, well, moves around when the point of S is there.
It is on board with final set.
Yes,
Because we put it on.
yes, but well, okay. It will never be like again. Yeah. Okay. And okay, now here's the example. Well, let's say I have just some space living over X. So the P factor. But I want this space to be equipped with a connection along X. So equip the connection. And as we learned, the correct way to formalize this notion is to say that it's descends to epsilon. Okay, but the point is that if you have a connection, it makes sense to ask whether or not sections of this space are horizontal. So you get, we're allowed to make the following definition, which is the space of horizontal arcs into this one. So this will be in this horizontal space. So this is a pre-stack and classifies the following data: a point of the round space and a horizontal section of Y at the formal disk around this point. Horizontal section of Y over X.
What do you mean by horizontal section?
So this is a very good question, and it's carefully been hidden. So what one has to show is that this space Vx actually itself emits a connection along X. So it actually descends to X the ROM. This is, well, intuitively believable, but I mean, yeah, requires like, well, formally speaking, I would have had to tell you how to do this, but I don't know.
We define it for S points over R.
Yes.
What else would it take to make it descend over?
Sorry?
What other meaning is there to the words it descends to R?
No, descend to X the ROM. So dx maps to X, and the claim is that actually it descends to X the ROM. Yeah, this requires justification, and I don't want to do it. But I mean, the intuitive picture is that if you have a formal disk, you should know what it means to be horizontal. Okay. Any other questions? Great.
Actually, what do you mean by decentering variable?
It means I'm just given some space over X the ROM, whose pullback to X is.
Oh, it's okay, fine. Okay.
What?
So let's grasp the R.
Well, maybe if you work in the opposite category, you would say this. But I don't know. Oh, sorry.
It should be X maps to X around.
Yes. Okay. So yesterday, this example already appeared for a very special choice of Y, namely the constant family BG times X. So for Y being just a constant family whose fibers are BG, this kind of has a tautological connection because it's a constant family. This was precisely the definition of what was denoted point mod G sub RON. This. So who's this? What was denoted by alpha? Now, since I have this, actual factorization space, I can produce from it all sorts of other things. I can produce a factorization category just by taking, say, encode star on it, so. Star. Right. Is a category. And I can also produce some factorization algebras in here by sort of topological sequence. So if I take the structure piece, which is something that makes sense in this category, is a factorization algebra. This. Now let me say something about the factorization structure on this space. So if you think about what the space is doing just at the level of k points, so if I have, x1 through xn, k points, and I'm asking for horizontal sections near these points, well, any horizontal section kind of is determined by its value at the central fiber. So the pointwise fibers of this space are really just products of copies of y. So, write it as a remark here. And that's the fiber of this funny space. X1 is one, and it really just the product of y. But something very maybe non-trivial is happening when these points are allowed to vary. So if, for instance, y was just like A1, you would get some very strange space over maybe x squared, because like a fiber at two disjoint points is A2, and like along diagonal somehow becomes A1. That goes is based on something here.
Can you just explicitly remind us why we're supposed to be shocked and dismayed by that type of behavior?
Well, you may or may not be shocked, but one thing you learn is that, the dimension of fibers is only allowed to drop, it's not to decrease. So this would appear to be a contradiction in mathematics. But this thing that you learned actually has hypothesis, which is finite type. So this family, even though like all of its fibers could be finite type, the family itself will not be a finite. Okay. So this is like one reason why we need some fancier notion of positivity. So now there's so in addition to this, now I can kind of play the same game with the puncture system. And because for reasons of insurance, I'll now also assume that y is your house. Otherwise, you don't get it. So I can also consider the space which parameterizes now not the horizontal sections over the non-punctured disk, but horizontal sections over the punctured disk. This is the pre-stack which classifies the private bonds and horizontal section. Over. And now, like the Keel's question is particularly relevant, so I don't know. You really do have to do some thinking to see that this answer is actually wrong. But okay, it can be done this time. Okay. And this space, well, it is not unrelated to the previous one. So you had a horizontal section over the non-punctured disk, restricted to the punctured disk. So there is now. Maybe I'll pull up iota from horizontal parts to horizontal roots. And this map is compatible with factorization. So push forward on this map. is a functor factorization paradox.
So
This one. We'll start. This plus like one. We'll start. One. Factorization. In particular, I could apply this function to my previous quasi-tautological factorization algebra and get a factorization algebra in this bigger category. Yes. I will start. What the is a fact.
Nice question.
Yes.
So what's the importance of the assumption that y over x is alpha?
So it's so that I can write this word. So if this pre-stack is not sufficiently well behaved, I'm not allowed to write this. But you should just ignore it.
That's the result next to second whole parts of the thing.
Do it Gerbier style. So here's x. Here's my space y. I live over x. Then I'm looking at the puncture disk around, well, maybe several points of x, but you know. So let me draw x topologically. So really, I'm looking at a puncture disk, and then you have a section. Okay. Now, because y has a connection over x, you can ask whether or not this section is horizontal with respect to the connection. That's exactly what I'm avoiding. So,
You say it's just a section over x around, but it's a section over x.
well, but like it's over the puncture disk.
It's a section over, okay, puncture disk around, that's the descent of the puncture disk to the.
Yes. Yeah, but like I didn't.
But if you're just wondering what is horizontal,
Yes.
it's a section over the round instead of multiply.
Yes.
And essentially it just means that there's some right flag such as phi of
Yes.
around to x is one that's the yeah.
Yes.
And, yeah, and a fun exercise is that if you do all of this in coordinates, then it all looks like non-linear systems of these, and then horizontal sections are just polynomial solutions to this.
all of this has a classical counterpart where connection just means subspace and the tangent space, and horizontal means that the differential maps to this subspace.
Yeah, I did learn classical counterparts weird.
Okay, All right.
Yeah, wait, so let me just like in the case with y is acting over x, with a whatever it's y over x equipped with a connection between like we have some the usual sheaf of algebras both of y on x, a usual algebraic curve. Then you also know how to differentiate from elements of it, a vector field x, and that satisfies the light. And then it's horizontal section just means a map to OX that means with differentiation.
Yes, so the level of informal gets that definitely is global. Yeah. Okay. So here was that one. Yes, okay. Yes. Okay, so the one thing I might point out is that this what kind of space is this? Well, the other one, horizontal, the horizontal loops. So general. Look at. So even if I just look at what's happening at a single point. There's some space. So because I'm not requiring that my sections are defined over the entire disk, the nature of the space will be that it's an instant. Or that scheme of it. And so we want to somehow maybe explicitly describe what is achieved on this. So what is in star of equations. And because it's of infinite type, we should not expect that it's going to just be like modules over some ring. You might expect it to be modules over a topological ring or something like this, but don't expect it to be literally modules over some ring. But the factorization formalism allows you to talk about or to access, say, encode of this, maybe in more directions. And for that, I will need another definition. So factorization. Module. Oh, sorry, we find an auxiliary space first. So let me to the point of the curve. And I'll write grams of x with the following variant of the Ron space. So this parameterizes the point of the Ron space, but with the additional condition that my subset Y contains this chosen point little x. So that. Okay, now here's the definition. So factorization model. For factorization algebra. And again, this definition will also make sense inside any ambient factorization category. Cran is well, so it's going to be a D module on this space. Or generally little section of C, but over lots of X. Called M. With kind of module version of factorization problem. So the fiber M at a disjoint union is supposed to be okay. So let's say that Y contains my little x, and then Y prime necessarily does not contain little x. It's supposed to be Y, and that Y cancel with algebra. So for one x, Y prime and one just. So again, secretly, what you should think is that the fibers of this factorization module at, let's say, x and y1 and yn. It's just some vector space at x, or object of this category. And then at all of the other points, you attach the algebra. A y1. A.
How do you distinguish the distinguished point in a way? Do you just say one of these points is distinguished and then all the other ones are okay, it's part
I just
okay.
I just chose one.
How are we supposed to think of it as a module? Like, in what sense is A acting?
I'm going to avoid this question. So,
So here actually X was a point of the run space
so
in the last.
where?
So when talking about factorization modulus, so do we have some fixed point X of the curve, or do we allow it to like be a
Currently
point
X
of
is
the run?
yeah. So currently X is the choice of point of the curve, but more generally, you can consider X to be any point of the run space.
There will be no. When you say that, so X is fixed, and we consider the distortion factorization module, then we'll be asking what sense is of the module, whether we call it module coming out. But here's the answer that this book, it proves that this exact node factorization module is equivalent to the notion of ether module for an ether module. That translates to module. Yeah, that's the answer. That's what I'm holding.
But it's also just the picture that like if you take a point near your fixed point, insert the element of the factorization off at that point, and you collide that point with the central point. That's the action.
In some sense.
In some sense.
Well, nobody asked why factorization now, there's other elements. But they got it, having it that open from.
So yeah, okay. When we talk about algebras, we usually imagine that there's some kind of binary operation which plays the role of the products, and maybe something confusing here is that there's no obvious binary operation. Yes.
In factorization models, we can cover that we have factorization models.
Not to my knowledge.
Those are the questions. What was the question? In factorization models, we covers the category of factorization algebras. Yes, that's the full class.
Okay. Well, okay, I think that minutes. So. Yes, okay, so yeah, there's no obvious sense in which A carries a binary operation, but behaves as if we're an algebra itself. Okay. So now, so here's a plan. Let's take it. Maybe here's the topological example. So if I take any factorization algebra, I can restrict it to this branch of X, and it's just automatically a factorization model. The branch of X is a factorization model. But now let me try to explain a more substantial example. Going back to this situation with horizontal loops. So here's the plan. So if I look at the info at my point X, I can just take global sections. So global sections that produces vector space. And I claim that this vector space can be realized as a factorization module for this funny factorization output. So it's the fiber at X of a factorization module for this structure. So no. This is my notation for the category factorization modules over this factorization module.
When you say one the vertical area, the five.
Yes. This is fiber at X.
Let me just, sorry. Yeah, so like, we also like think of factorization modules sometimes of like have this m sub runs of X, because distinguished runs that have distinguished point in X itself, where we can take a fiber. So the factorization module has an underlying vector space under that fiber. And we sometimes think that factorization module is that vector space they done with an additional structure. I mean, we extend it then rounds of X, and we know all the other fibers, the logical structures, how to move them together.
Yes. Okay, I guess that's. Well, what this also be. Okay, so okay, so maybe there's a small misnotation here, so. This guy originally lived inside info of L plus Y. Now I'm regarding it as just a factorization of the as is. So maybe including. So this one on the global sections. But if I probably the same to you. Okay, so what's the mechanism for this? Well, okay, so I want to start with an object here and somehow tell you how to kind of insert the factorization algebra at all of the other points. And so it suffices to do the following. So suffices to define a functor. Let me call it insert vacuum from my source category to, well, something that lives over bonds of X, which fiber-wise just inserts this guy. So which fiber-wise it forms this set F to F box the North Star and my comments. Okay, and so the mechanism by which, well, okay, so if I have such a functor, I just compose it with global sections of rounds of X and I'll get my factorization model. So the question is, how do I actually do this? And here's the key input. With the following geometric assertion, which relates, well, the puncture disk at X to the puncture disk at Y for any Y containing X. So, Y, well, maybe Y is a puncture of X. Here we have, on the one hand, there's the puncture disk at X and the puncture disk at Y, and they're related by the following. So I can take a formal disk at Y and just remove only the point X. And now if I look at horizontal sections over these three. Well, on the one hand, I have horizontal sections on the puncture disk at X, or horizontal sections over the puncture disk at Y. But there's this intermediate space, so it's horizontal sections over this side. So I don't have any better notation for this space. And that's both of them by restrict. So now I can pull back, push forward, and that's my functor. So this produces functor from input star. Well, and as y varies over rods of X, I obtain the definition of this. And now my Okay, so let's see why this does what we wanted. What exactly is going on here? Oh. So what is happening pointwise? So if I just choose, y1 through yn, so at x is the union y1, yn. What do we get? Well, these disks, well, I have the punctured disk at x, and then I have the punctured disk at x, which the union of the punctured disk at equal y's. In this intermediate space, I have the punctured disk at x and then the non-punctured disk at all of the y. And so then when I take horizontal sections, the space in the middle, well, I get so horizontal sections over the punctured disk of y at x. But then at all of the other points, I have non-punctured disk with y. So this pull back push forward functor. So starting with something here, well, when you pull back, you just produce O at all of the other points, and then just push forward. That's exactly what we want. Okay. Now let me state a theorem. Okay, so we have this number. And so and factorization models. The theorem I want to state is that this is an equivalence capacity. Although it's not quite true, so I want to do some declarations. So the first declaration is that, okay, so both of these categories have natural T structures. So for this, it does not define it, but there is a natural T structure on this.
You're repeating the assumptions of y.
F1 over x. Then there's finite assumption.
Finite circle.
Well, it's finite type of a non-trivial set. So and right. On the target, there's a T structure coming from the forgetful functor to vector space. You just take the vector. And this is an equivalence of categories on the eventually equivalent. Then okay, where it ends that talks. Sure. It's by this mechanism that, well, we'll be describing the category spins. And there's a maybe, well, more formal kind of encoding of this kind of structure, which is called unit element. Say what that is. Category. So first there's some factorization algebra. It's called the factorization group. So algebra. Units. Units.
So Kevin, you just say it in like the word, so like, how are we gonna use this thing to do with above?
You will see in the next talk. So
The second thing about this, are we supposed to think about this as the greater than minus infinity part would be sort of Q if we didn't have all this factorization stuff, and that's kind of like modules over.
it's kind of on the left.
Yeah,
So you try to say this therefore Pico, but you would also need to put greater than minus infinity. So the issue is this. Okay, you cannot write Pico on the left. Okay, that's not the kind of thing that you want to do,
I asked this like a lot.
which is whether or not you should imagine that it's equivalent of Pico.
No,
Can I make a comment about this? So just like, okay, this loop space thing, what you should think is it looks like sort of an pro affine space. So if you just had that like pro affine space that came up in Demas talk, that's just stack of a polynomial algebra in infinitely many generators, x1, x2, x3. When you do the int, you add guys like x minus 1, x minus 2, x minus 3, but then you allow certain infinite sums in those directions. And so when you think about it, you only want to consider modules where like sort of topological modules of that algebra. Each vector should be annihilated by most of the x minus n's. And so that's some just like naive category you have in mind. It's not quasi-co necessarily on that thing, which like what is quasi-co on an n scheme at the abelian category level. It's actually kind of hard to really define an abelian category of quasi-coherent G's on an n scheme. The derived category is great. And if you just kind of think naively about the definition I said, it's sort of like you have what's definitely allowed is a module and some sub-scheme of that loop space, or some bigger sub-scheme of that loop space. And you're doing some kind of like gluing procedure of all of those, or some co-limit procedure of all of those categories. And that's what this int co-star is designed to do, is to express the idea of topological modules over the ring of functions here. So not just arbitrary modules, which would only really be what you would like. That doesn't even really quite make sense, but it's also not. It's not really the thing you get from quasi-co anyway, but it would be the thing you got from quasi-co in the affine situation. But this is designed to express the idea of discrete modules over the topological. Yeah.
Okay, so any other questions? Okay.
So in other words, quasi-co sounds great, but then if you actually kind of like look at it very closely in certain situations, you realize it's like not always the most natural thing for a certain problem. That's what this is.
Okay, let's see, and basically the ability to do this, or the ability to something the boundaries to x. And boundary. Again, with the still denoted in stat. Yeah, let's see.
This A,
Oh, sorry, units.
Can you modify the space on to a convoluted anomaly?
Yeah. So. But what you'll get is a pre-fact value, not in sets, but in cosets.
So this will be exactly done in next talk tomorrow. You'll be one. It'll be all about that.
Yes.
By the second thing, you just mean that there is this counter insert vacuum that looks like this underlying.
Yes. And of course, they're compared to the
Yeah.
And this should happen for every, so strictly speaking, X should be allowed to be any point beyond 60. But again, maybe for now, let's see. Mention this. Okay. So here's another example, which is also very important, which is the category of Casimidi modules. Your beer ingredients. I'll use the notation group that now. So. However, this was defined, it involves while the loop space of your group. So it's okay. One can believe that this category makes sense as a factorization category. So the factorization category. And furthermore, it has a unital structure. So in this example, the unital structure came from, well, kind of thinking about, well, the non-punctured disk versus the punctured disk. And maybe it's somewhat believable that this category should have a factorization unit, which has to do with not the entire loop group, but just the positive loop group. So with factorization.
The first example is unit or whatever is this info X thing.
Yes.
But that O thing.
And I put what? Yeah, that was the original example.
Yeah.
And this is like the axiomatization of this example.
Yes.
Yes, that's that was the motivation that I said for this. So now, let's do this unit structure. Well, I'll just say with units, the vacuum, which for consistency, I'll use the standard notation. And furthermore, so previously we had this global sections functor. Went to vector spaces, and this functor was factorization functor. Any Casimidi module has an underlying vector space, and that forgetful functor is also compatible with factorization. The other version is that I'll just forget to the underlying vector space. So okay, if I was very responsible, I'd write the subscript run everywhere, but someone to stop writing this. Factorization function. And what this buys us is that we can just play the same game as before. So you like start with your Casimidi module, you do this inserting the vacuum everywhere else. They just look at the underlying vector space. What you have is a factorization module with the factorization algebra. It's obtained by taking the underlying vector space of this vector space. So by look at the underlying vector space of the vacuum. So this is a factorization algebra. And careful functor. Select. It lists two factorization modules strictly. And very similar to this theorem, this functor is also an equivalence of categories. Or is equivalence on eventually the negative part. Okay. So I think I'll stop there. Any other questions?
So